6 you have exams. You know, I never postpone that. So you should know from now that at week 6 you have other class tests. I know that maybe for other modules also you will have, but for this module you won't be postponed. Okay? So then it would be 25% of your mark. It consists only the analog part until week 4 that I teach you. Week 5, if I could finish completely analog, then you will have all of them. Otherwise, we will review. At week 5, generally, I review for the class test. See what happens. But we cover most part of analog part in the class test. Then we have lab coursework. We have 2 courseworks. At the first 6 half of the 6 weeks of the semester, you have simulation of analog electronic. You use LTS files. I know most of you know that. In the lab, also the lab administrator will teach you. Then you will have 2 separate coursework that you should write a report for both of them in one report. Okay, at week 7, you will write the report. Okay, the first part of the coursework, it's only simulation of LTS files of analog circuits. Then the second half of the semester, you will have practical coursework. You will have probably 1 or 2, or sometimes depends on the time we have, depends on the number of students and facilities we have, 3 circuits that you should implement practically, okay? So I divide you in the groups on that time, at least 2 in one group. You will do the measurement, you will do the practical implementation, but individually you will write the report, okay? So it means that at the end you will have 2 reports for the coursework. First report week 7, second report at the end of semester. Then we will mark you, and it would be 25% of the module. So imagine 50% class tests and lab coursework, and the final exam would be 50% of your mark. The final exam covers all of the topics of 12 weeks, okay? So there is a structure for that. You can find the previous exams, almost we follow the same structure. You will have 6 questions, 3 for analog part, 3 for digital part, and you will answer 2 of them. 2 for the analog or 2 from digital. It means that at the end you should answer 4 questions, okay? Each question 25%, final mark would be 100 for the exam. And I emphasize the parts that are more important for you. Also, we have a tutorial. Next week we start tutorial. I already uploaded the tutorial question for you in the week 1 folder, as you see. So you have 1 week to solve that. Then I will solve in the tutorial session, then I will provide the solution for you in the blackboard, okay? So it means that you have always 1 week time to solve the tutorial questions yourself. I expect you solve. When I come here, I check, and I give you the half session of the tutorial for you to check your solution with your friends. It means that 1 half of the session would be your solutions. You will work on that, you complete that, and the second half of the session I will provide the solution for you and explain, and then after the session I will upload in the blackboard the solution. So you have questions, and after that, solution. It's the style of the module. I hope it will be good for you. Then, as an overview, I can tell that for the analog electronics that we start with that after reviewing the numbering system and digital logics. You will, we start with digital. I mean that first 6 weeks are digital electronics. You will simulate digital circuit with LTS files, and you implement the analog circuit through the practical implementation. For the digital electronics, we have numbering system, we have Boolean, algebra, and logic gates. We have gate level minimization. This is important. We use Carnot map for that. We have combinational logic and sequential logic. At the end, you will know how to design the digital circuits, and also with the simulation. Slowly we go to the advanced circuits. You will complete this part. And then we have an analog electronics part. We will study the transistor. I know already you know transistor. I teach you mainly BJT, but we will study the FET, and then BJT amplifier circuits, operational amplifiers for op-amp applications, active filters, and Wayne bridge oscillators. Generally, in the practical part for the coursework, I give 2 or 3 circuits consist of active filters, op-amp applications, or Wayne bridge oscillator. This is the practical implementation part of the module. So, I know all of you know the numbering system, but we will review that because it's the base of digital electronics. You should have good information and idea and knowledge about the numbering system to design the digital electronic circuit. The numeric system we use daily is decimal. We know that in our mind always we use the decimal. And we count from 1 to 9. We have 10 digits, 0 to 9. And based on that, we count everything in our mind and in our daily process, mathematical process. But imagine, when we talk about digital electronics, we talk about computer, mobile, calculators, and you know, every day with the advancement of technology, they are more important in our daily life. They don't work based on our mind. No, there is a difference. So they work mostly based on the different numbering system. This system is, our mind system is not conveying information, since the information is handled codified in the shape of on or off bits. We know that at the end, at the base of digital electronics is based on off-on bits, 0, 1. We know that, okay? So in this case, it doesn't work such as our mind to consider 0 to 9 decimal calculation based on the decimal. So we should define a new system for them. What is this system? It's a bits, 0, 1. A base of number system defines the range of values that a digit may have, okay? But based on this 0 and 1, based on bits, we can design several process, calculations, everything. So what's the difference and what are they? So a base of a number system defines the range of values that a digit may have. Generally, we have three systems for the machines: binary, octal, or hexadecimal. What are they? What's the difference of them? The binary system is based on 2, okay? There can only be 2 values for each digit of a number, either 0 or 1. So in the binary system, we have only 2 digits, 0 and 1. We have not any more digits, okay? Then for the octal system or base 8, there can be 8 choice for each digit of number, 0 to 7. Okay, we have 8 choice. It's base of 8 from 0 to 7. And in a decimal system or our mind system, we have base 10. We have 10 digits, but they start from 0 to 9. All of the numbers we have in our daily life are based on these 10 digits. And then we have a hexadecimal system. We have 16 values for each digit of a number. We have 0 to 9 as decimal, but we have extra digits. How we can represent them? We can represent them by A, B, C, D, E, and F. What is A? Can you tell me?
10.
B?
11, 12.
13, 14, 15. Perfect. So, as you see here, we have 4 systems as a summary: decimal, binary, octal, hexadecimal. The base of decimal is 10, base of binary is 2, base of octal is 8, and base of hexadecimal is 16. The symbols that we use for the digits in decimal, 0 to 9, for binary 0 and 1, for octal 0 to 7, and for hexadecimal 0 to 9, and then A, B, C, D, E, F. So, which of them is used by humans, by us? Only decimal. And which of them used in computers? Binary, octal, or hexadecimal. Depends on application. And the interesting point is this: when we talk about the machine system, yes, here we have 0 to 7. But again, each of them represent by 0 and 1 only. Okay? So, decimal numbering system. I start with the logic of this decimal numbering system and we go ahead with other bases. Generally, the human brain is most used to using a decimal system. We know. Each digit in number represents an increased power of 10. So imagine 0 would be 10 power 0. Sorry, 1 would be 10 power 0. Then 10 power 1, 10. 10 power 2 or 10 square, 100x. So even this, we don't consciously think of an increasing power. Okay? So now I want to represent how the decimal logic works. We have this number, 241. What it means, we start from the right part, right digit, or lower important part, lower priority part, 1 times 10 power 0. Then 4 times 10 power 1. Then 2 times 10 power 2, and we can extend. Depends on the digits we have. So it would be 1 times 1, 1. 4 times 10, 40. 2 times 100, 200. Then we add them, 200 plus 40 plus 1, 241. This is the base of decimal system. So, but what about the binary? You see, when we talk about the base, it is important. Base is important for us. If you follow the base, everything would be straightforward. Imagine we talk about decimal. Base is 10, then we start 10 power 0, 10 power 1, 10 square, continue. When we talk about binary, the base is 2. It's the same, 2 power 0, 2 power 1, 2 power 2, continue. So here, imagine, we have this decimal with this binary number, 11001. As you see, we put this index as it's a binary. So we follow the same, 10011. Then 1 times 2 power 0, 1 times 1, 1. 0 times 2, 0. 0 times 4, 0. 1 times 8, 8. 1 times 16, 16. We add them. 16 plus 8 plus 1, 25. So it's equivalent. Clear? So solve this yourself. Can you give me the answer? We have this binary number, 1, 0, 1, 1. Give me the equivalent. I go a bit fast this part, but I ask you also to solve some of the questions. Because I want to be sure you get the point.
Would you like any pages for taking
What?
notes?
But you can count in your book. 11. You see? 1 plus 2, 3 plus 8, 11. Yeah? The answer is 11. Yeah? So, you see, as you see, we follow the same rule. 1, 1, 0, 1. 1 times 1, 1. 1 times 2, 2. 0 times 4, 0. 1 times 8, 8. So imagine this is 1, 2, 4, 8, 16, 32, 64, and then you can continue. The answer would be 11. Can you give me the answer of this one? 1, 0, 0, 1, 0, 1.
37?
What?
37?
37. See, I should. Yeah? 37? Agree? Okay. So most of the students agree, then we will see the answer. So we do the same. You see from the right, 1, 0, 1, 0, 0, 1. Then 1, 2, 4, 8, 16, 32. 1 times 1, 1. 0 times 2, 0. 1 times 4, 4. 0 times 8, 0. 0 times 16, 0. 1 times 32, 32. Then we add 32 plus 4 plus 1. 37, as your friend found. So, another one.
241.
What?
241.
Because you see the answer. That's okay. So you see here, in another way I do that. 2, 1, 2, 4, 8, 16, 32, 64, 128. As you see, 1, 2, 4, 8, 16, 32, 64, 128. Then we multiply. 1 times 1, 0 times 2, 0 times 4, 0 times 8, 1 times 16, 1 times 32, 1 times 64, 1 times 128. Then we will add them. And the answer would be 128 plus 64 plus 32 plus 16 plus 1, 241. Is it okay? Yeah? Clear? So, I can ask here, you don't have the answer, so I can ask you to solve the third one, only third one, because I don't want to take more time for this, but give me the answer. Then I will solve. Then I suggest you solve the 3 others in your home and check with your friends. This is my experience. If you are active in the class, if you follow me, if you solve the question I ask you, 100% you get very good marks in the exam. But sometimes I see that some students don't come, they are not very active, so it's a bit a struggle for
173.
What?
173.
One?
How long was the timer on?
173. See.
See the timer for the login? How long was it on for?
1, 0, 1, 0, 1, 1, 0, 1. And you count with your mind only. 1, 2, 4, 8, 16, 32, 64, 128. Then we have 1 plus 4 plus 8 plus 32 plus 128. 5, 13, 45. Yes, 173. That's true? Yeah? Okay? Clear for all of you, or I should explain more? Clear? Okay. And this is the easiest one. What is this? Tell me. 5. Yeah. Okay. Now we want to know how we can convert decimal to binary. It is important. Because always we work on the decimal, but the machine works on binary. We should know how we can represent the numbers in our mind in the machine. So, I give you one example, then based on that, you will follow me and you will. I know already you know what will do. So, we want to convert 61 to binary number. In this case, we will divide the decimal number to the base. Here the base is 2. If you want to convert to the octal, it would be 8. If you want to convert to hexadecimal, it would be 16. Here the base is 2. We divide decimal number to the base, we find the quitant and remainder. We keep remainder, and then again we divide the quitant to the base, next quitant to the base, until the value would be less than base. Then we keep that at the quitant. So see, 61 over 2, it gives us 30 plus 1. We keep this, then 30 over 2. Next. It would be 15 plus 0. Then 15 over 2, 7 plus 1. Then 7 over 2, 3 plus 1. Then 3 over 2, 1 plus 1. Then 1 over 2, 0 plus 1. Here we stop. When our quitant would be 0, we stop. Okay? And then we have this. Can you tell me we should start from up or down? Bottom or top?
On.
What? Top. C. Yes. We start, the top one goes to the right. And the last one goes to the left. Okay? So this is the answer. When the quitant is 0, we stop and we consider the remainder for the whole number. So this is the equivalence in the binary of 61. Okay? So, another example, 107. I give you another example, then I will ask you to solve. 107 over 2, 53 plus 1. 53 over 2, 26 plus 1. 26 over 2, 13 plus 0. 13 over 2, 6 plus 1. 6 over 2, 3 plus 0. 3 over 2, 1 plus 1. 1 over 2, 0. Yes, stop here and we have 1. So the answer would be 1, 1, 0, 1, 0, 1, 1. Okay? You see? 1, 1, 0, 1, 0, 1. So, there is another way. Sum of weights. The method is called as sum of weights. Convert decimal 241 to binary. What do we do? First, we find the powers of 2 that fit into a number starting with the largest value. I will show you. Then write the binary number with 1s in the bit position of these weights. Then the sum of these weights should be equal to the decimal number. So, how we can do this? Here, we write such as this. 2 power 0, 2 power 1, 2, 3, 4, 5, 6, 7, 8. Or 1, 2, 4, 8, 16, 32, 64, 120, 256. Okay? We write and continue. Then we know the value is 241. So we stop at 256. Why? Because we have not more than that. Okay? Because 241 is less than 256. Then we start. So, what is the largest power of 2 less than or equal to 241? 256. No, sorry, 128. It means that 241 is between 128 and 256. We put 1 here. Then we decrease this from 241. Okay? So, 241 minus 128 would be 113. Then we ask 113 is between 64 and 128. Then we put 1 here. Okay? So, we put 1 there. Then, now what we do, we decrease 64 from 113. 113 minus 64, 49. What's your idea? 49 is between 32 and 64. We put 1 here. Clear? And then 49 minus 32 would be 17. Again, 17 between 16 and 32. We put 1 beside 16. And then 17 minus 16 would be 1. Okay? So, then 1 would be here. So it means that this 3 should be 0. because 1 is between 1 and 2. Then we put only 1 at 1. Yeah? And this would be the binary, okay? So we have two ways to calculate the binary numbers from decimal. You can use both of them or each of them in the exam. So, I want to ask you the last one. Convert the 73 to the binary.
You can use the binary, right? That all needs their memory. Tutorial.
So, let me do that. So I use the second method because I think it's easier. 1, 2, 4, 8, I add 73. 16, 32, 64, 128. Our number is 73. 73 is between these. I put here 1. 73 minus 64 would be 9. So then 9 would be between 8 and 6. I put here. Then 9 minus 8 would be 1. Then I put here.
There's 4 in binary.
It would be our answer. Is it okay? Do you get the same? What? Because when we don't go to 256 because the number is 73. It's less than this. Then we don't need others. Others would be 0. The maximum of the 2 power x when it has this one, the first one. It's between 128 and 64. If we go to 256, it will be 0. So, now I want to talk about octal system. So, what's about octal system? As we know, we have 8 digits here from 0 to 7. Here. Each octal digit represents or replaces 3 binary bits. It's the main point here. When we talk about octal, as I told you, in the machine only knows 0 and 1, nothing more. Okay? So, in octal we have 0 to 7. How we represent them in the machine? With 3 digits. 3, 0 or 1, each of them. Imagine 0, 1, 0 would be 3, 0. 1 would be 0, 0, 1. 2 would be 0, 1, 2. So, the style of this is this. We have 0, 1, 2, finish. Okay? Then the digits would be between them. Sorry, no. We have 1, 2, 4. Because the maximum value would be 7. It covers 7. And then 0, 0, 0 covers 0. So, it's the style of octal system. The octal system makes it much easier for an operator to enter or read binary numbers. So, then we have 4 things to know. Octal conversion. Octal to decimal, decimal to octal, binary to octal, octal to binary. Remember, in octal, each digit in octal is represented by 3 digits of 0 or 1. It's important. And the form is 1, 2, 4. So, here, first, octal to decimal. When we want to convert the octal to convert to octal to decimal, we will do the same as decimal. Remember the base power 0, base power 1, base power 2, continue. Here we have 3 digits of the decimal, 472, 2 times 1, 2. 7 times 8, 56. 4 times 64, 256. We add them and it gives us 314, 314. It's the decimal number of that octal system. So, let's use octal number Can you calculate this for me? This is 241 in octal. Give me the decimal number. Two, 4, 1 in octal. We want to find in decimal. 2, 4, 1. 1, 8, 64. Okay? Or in other words, 2 power 0, sorry, 8 power 0, 8 power 1, 8 is 4. So then, 1 times 1, 1. 4 times 8, 32. 2 times 64, 128. We add them. 161 in decimal. Okay? Clear? See the answer. We have 2 for 1. Okay? Fine. Then we know the first right digit would be should be multiplied by 1. Then 8, then 64, which is 8 power 2. If we have more digits, we go to 8 power 3, 8 power 4, 8 power 5. And then 1 plus 32 plus 128. Remember, in your exam, you should have calculator. It's necessary for you. 161. So, another example. 7724, which is octal. We want to convert to decimal. We do the same. 4277. But here we have 1, 8, 8 power 2, 8 power 3. Because we have 4 digits. And then we can continue. 1 times 4, 4. 2 times 8, 16. 7 times 64, 448. And 7 times 512. Why 512? Because it would be 8 power 3. The answer would be 3,584. We add them, the answer would be 4,052. Clear? Yeah? Then, another example. Here, 361. Then, 8 power 0, 8 power 1, 8 power 2, or 1, 8, 64. Then we multiply. 1 times 1, 1. 6 times 8, 48. 3 times 64 would be 192. 192 plus 48 plus 1, 241. It's a decimal. Okay? So, now we want to convert decimal to octal. It will be the same as the binary. We divide by base. But here the base is 8. Okay, then we have quiescent, we have reminder. We keep reminder, we divide quiescent until the time that we have 0 at the quiescent. Then we stop and we use the reminder to make our value. So, here, our decimal is 349. We want to convert that to the octal. 349 over 8 would be 43 plus 5. You can use your calculator. Then you count. Then the first reminder would be 5. Then 48 over 8, 43 over 8 would be 5 plus 3. Then 5 over 8, 0. We stop here, we keep reminder 5. Then the answer would be 535. Clear? Yeah?
Oh wait.
This is 534.
What? Oh yeah, it's a 5.
Okay.
It's 5. I should update that in the... That's good. Yeah, there are sometimes typo you should see for me. Okay, the other request, example, 1267. It's a decimal. We want to convert that to the octal. So, first divide by 8. When we divide by 8, would give 158 plus 3. The remainder would be 3. Then 158 over 8 would be 19 plus 6. 19 over 8, 2 plus 3. And then 2 over 8, 0 plus 2. Then we keep because we have quicken 0. Then 2, 3, 6, 3. Clear? Yeah? Yeah. So, do you want to give you an example you solve or no? I go here. If it is clear for you, formula is clear, how we convert decimal to octal, yeah? Okay, so I teach you. Now we want to convert binary to octal and octal to binary. So, as I mentioned, when we talk about binary and octal, each 3 digit binary digits would be 1 digit in octal, okay? And the style is this, 1, 2, 4. So, here we want to make the binary to octal. We group the binary digits of 3 starting with the least significant bit. From the right, we start to group each 3 digits, binary digits, as 1 octal, okay? And then we, based on the rule of 1 to 4, we will find the equivalent octal 1. See how we can do that. So we have this 1 0 0 1 0 1 0 1. So from right we start. These 3 belongs to one group. These 3 digits belong to the second group. Here we have 2 digits. We can put 0 because 0 has no value. And then we have 3 groups. First, second, third. This one would be 1 2 4. 1 plus 4, 5. Okay? This 3 one would be 0, 1, 0, 1, 2, 4, 2. And this 0, 1 again 0, 2, 2, 2, 5. Clear? I will explain. But here, as you see, here I explain better. We have this. We have 0, 1, 0, sorry, 1, 0, 1, the first group from right. Then 0, 1, 0, second group, and then we have only 0 and 1. Then we can add a 0 because it has no value. Then we have 3 groups consist of 3 digits each. Then here 1, 2, 4, 1, 2, 4, 1, 2, 4. 1 times 1, 1, plus 1 times 4, 5. You see? Here, 1, 2, 4, 1, 2, 4, 1, 2, 4. You should know that. And then here, it would be 1 plus 4, 5. 2, 2, 2, 2, 2. Let's give you another example. This one. You see? Here we have this. How many digits we have? 1, 2, 3, 4, 5, 6, 8, 9, 10. Sorry. 3, 6, 9, 12. So it's easy because we have 4 groups. Okay? The first group, the second group, the third group, the fourth group. And we will do the same. Here as you see, we separate them. The first from the right, let's start 0, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, 1. And again 1, 2, 4, 1, 2, 4, 1, 2, 4, 1, 2, 4. And we will find the value. So here, the first, can you tell me what is this? 5. This?
0.
This?
7.
This?
4.
Perfect. You see? It's very straightforward. And you should follow this because you have some question in the exam from this. You see 4, 0, 4, 7, 0, 5. So now octal to binary. What's your idea? When we have octal, we want to convert to binary. We do the reverse. We know that each octal digit would be 3 digits in binary. And we know the rule of 1, 2, 4. Then we can find the equivalence. See, for example, this. We have 1, 2, 6, 7. They are in octal. We have 4 digits in octal. Can you tell me how many digits we have in binary? 12. Because we have 4 digits in octal, 4 times 3, 12. So each of these should be represented by 3 digits in binary. Okay? We have 7, 6, 2, 1. And then we have 1, 2, 4. 7 would be 1, 2, 4, 1, 1, 1. 6, 1, 2, 4, 0, 1, 1. 2, 0, 1, 0, 1, 1, 0, 0. From the right, I tell you. So you see here, based on the 1, 2, 4 rule, 7 would be 1 plus 2 plus 4. Each of them should be 1. Then 6 would be 2 plus 4. What it means? It means that for 1 should be 0. 2 would be only this, 1. And 1, 1, 0. Clear? Yeah. Do another example. So can you convert this yourself? How many digits we have? 12 again. I think also you will need break. After 5 minutes I give you break. Let me complete. Honestly, digital part is easy. If you follow me, all of them, yes, every session we have more advanced, but if you follow one by one, Analogue also the same, but you saw?
I guess they're going to be okay about that shit again, I'll cry.
So you are interested in taping on with us now, aren't you?
Fuck the headache.
So, see, here we have 4 digits. It means that we have 12 digits in binary. Each digit is represented by 3. 7 would be based on the 1, 2, 4, 3, 1, 1, 1. Then 2 would be 0, 1, 0. Then 0, all of them 0. Then 4, the 4, 1, then 2 and 1, 0. So you see here. I explain again. We have 7 based on 1 to 4, 1 plus 2 plus 4, then all of them should be 1. 2, only 2. 0 times 1, 1 times 2 plus 0 times 4, then here. 0, all of them 0, 4, this is 4, 1, and 1 is 0. The hexadecimal will be the same, but in the hexadecimal we have 4 digits instead of 3. So, yes. Now I teach you the hexadecimal and then I give you break to go to the digital logic, or to read the digital logic that you know already. So, in the hexadecimal, we have 16 as the base. Then again, here we have 0 to 9, then 8 to 11. The hexadecimal digits of 8 to 12 are equal to 10 to 15. You know already. Each hexadecimal digit replaces 4 binary. Here, instead of 3, we have 4. The same. Then 1, 2, 4, 8. Everything will be the same. Hexadecimal to decimal, we will follow the base rule of 16 power 0, 16 power 1, 16 power 2, 16 power 3. Then decimal to hexadecimal, we divide the hexadecimal 1 by 10. Sorry, the decimal 1 by 16, quick and reminder. For the binary to hexadecimal and vice versa, we use the rules of 4 digits for each digit of hexadecimal, do the same 1, 2, 4, 8. So here, hexadecimal to decimal. We will follow the rule of this, 16 power 0, 16 power 1, 16 power 2, continue. Okay? Here. So imagine, we have 2EB. What it means? It means that 2E and B. What it means? B is 11, remember? E is 15, I think, yeah? So, you should consider this also. Then we have 16 power 0 for 8, 16 power 1 for E, and 16 power 2 for 2, as you see. We can continue what others are useless because we have not more digits. Here we have B, which means 11 times 1, 11. E, 14 times 16, 224. We have 2 times 256, 16 power 2, 512. Then we add them. Okay? And it gives us the answer, 747. Another example, CAD. D would be 13, A would be 10, C would be 12, okay? And then we have the same rule. For D, we have 1. For A or 10, we have 16. For C, we have 16 power 2. So then you see, here, 1, 16, 256 times 13, times 1, 13. 10 times 16, 116. 12 times 256, 3072. We add them, and we find the answer. 3245. Is it okay? Clear for all of you? Yeah, perfect. So decimal to hexadecimal, what should we do? Divide by base. The base is 16. Okay, here, for example, I give you example 475 in decimal. What will be the hexadecimal? Over 16, 29 plus 11. 11 would be B. Then 29 over 16, 1 plus 13. 13 would be D. 1 over 16, 0. We stop plus 1. Then 1 dB. Okay? For the second one, 584 over 16. We divide by your calculator. You can find quotient and a reminder. 36 plus 8. Then 36 over 16, 2 plus 4. You know, 2 times 16, 32. 36, 4 is reminder. Then 2 over 16, 0. Quotient, we stop, and 2 would be reminder. Then 2, 4, 8. Here? Yeah? And binary to hexadecimal, each 4. We classify as 4, 4, 4, the binary numbers, and find the equivalent hexadecimal digits for each 4 numbers. For example, here for a series, we have 1, 0, 0, 1, 0, 1, 0, 1. We classified by 4, the first group, the second group. And then 1, 2, 4, 8. And we find the equivalent. Okay? Here, we classify 4 by 4. Then 1, 2, 4, 8, 5. 1, 2, 4, 8, 9. 9, 5. You see? And then this one, we have more, we classified again, we have 12 digits, we classified them in 3 groups, the right, from right, 0, 1, 0, 1, here, then second one, 1, 1, 0, 0, and the last one, 1, 0, 0, 1. Then again, 1, 2, 4, 5, 4, 8, 1, 2, 4, 8, 5, 1, 2, 4, 8, 12, would be C, 1, 2, 4, 8, 9, 9, C, 5. Clear? Yeah?
Yeah.
And hexadecimal to binary, again, here we have 4 digits in hexadecimal. How many digits we have in binary? 16, because here we have 4. Then 5, 1, 2, 4, 8. Count, 1, 0, 1, 0, 1. F, 15, all of them 1. 8, 10. 1, 2, 4, 8. 2 plus 8 would be 1, 0, 1, 0. And 1, 0, 0, 0, 1. Clear? 1, 2, 4, 8. Remember, I show you. 5. Based on 1, 2, 4, 8. 5 would be 1 plus 4. Then 1 plus 4. 1, 1, 0, 0. Then F. 1 plus 2 plus 4 plus 8. All of them 1. 8, 10. 2 plus 8. You see, 2 plus 8 is 2, 0. And 1, 1, 3, 0. Another example. Solve, please solve this, then I give you break. D0, E8. Find the binary formula. Remember, hexadecimal, each 4 digits. 1, 2, 4, 8. One, 2, 4, 8. 8 would be 1, 0, 0, 0. E, 14. 1, 2, 4, 8. 4 plus 2 plus 8. 1, 1, 1, 0. 0, all of them 0. D, 13. 1, 2, 4, 8. 1 plus 4 plus 8. Then 1, 1, 0, 1. Yeah? This is the answer. 8 would be 8, then 0, 0, 0, 1. E would be 13, 14. 2 plus 4 plus 8. 1, 1, 1, 0. 0, all of them 0. D, 13. 1 plus 4 plus 8. 1, 1, 0, 1. Clear? Yeah. How to add binary data. Now I give you break, then we come here. After this is more important. How many minutes? 15.